These videos take a long time for me to save and upload, so they won't be up tonight. Hopefully they'll be up by tomorrow night. Okay. So we say that chemistry is the study of matter and energy. Two very different things, but we consider those two things to be what chemistry is about. This is Chemistry Cat. How many people have seen Chemistry Cat before? A few of you. You'll see a lot of Chemistry Cat. Okay? Last semester, a student actually made a Chemistry Cat trophy for it. Okay? So you will see that, and you'll have the option, not the option, the chance to, on paper, win that trophy and write your name in the book, and you can live in infamy. Okay? But that'll be at the review sessions. So you need to come to the review sessions if you want to win the Chemistry Cat trophy. It looks really good. You'll have to be there. So we say that chemistry is made up of matter and energy. Okay? Matter is anything that takes up space and has mass. I realize that's a vague definition. Okay? But the concept of matter is, even though it physically exists, the concept of it is a man-made idea. Okay? So if it takes up space and it has mass, we call it matter. If it's something, it is matter. Energy is not matter. The energy primarily that we're going to talk about in this class is heat. Heat is not matter. Light is not matter. They don't take up space. If you've taken physics, you may know that some forms of energy have mass. They have momentum. That's beyond us, okay? But very clearly, light and heat don't take up space, so they have no, so they are not matter. If it's something, it's matter. So this is a picture. What forms of matter, what things that are matter do you see in this picture? Cars, buses,
Everything touching the ground.
Anything touching the ground,
The ground itself.
the ground itself,
The bridge.
the bridge,
Buildings.
buildings, people. What do you see but don't actually see? Air. Air is, that's matter, okay? It's just gas instead of a solid or a liquid. What forms of energy do you see here? The light coming out of the light bulb. The light bulb itself is matter, but the light coming out of it is energy.
The heat from the cars?
The heat from the cars,
The light from the sky.
light from the sky. What else?
People walking on the bike?
What kind of energy is that? Why is that energy? Kinetic energy. Well, we'll talk about kinetic. Kinetic energy is the energy of movement. So anything that's moving has kinetic energy. Anything else? I think you pretty much covered that. So, if we say that matter and energy are chemistry, what in this classroom is related to chemistry?
Everything?
Everything. Everything in here is either something, so it's matter, or it's energy. So everything in here is related to chemistry. Okay? If you wanted to categorize the things in here, how could you do that? Make up your own category.
Organic versus non-organic?
Organic versus non-organic. I'm guessing you don't mean no pesticides on it.
Yeah, well, you get that.
Yeah, no, I know exactly what you mean. I know exactly what you mean. How else could you categorize things?
Moving or being still.
Moving or still?
State.
What do you mean? What do you mean?
Solid. Gas.
Solid, gas, or liquid?
Animate. Inanimate.
Right? Alive or not alive? I mean, we can come up with a lot of different ways to categorize things. What we're going to talk about today is mostly how chemists categorize these things. I mean, you can say there's green things and red things and categorize them by color. You can do anything you want. So we're going to start here at matter, and we're going to work our way down. It's going to keep splitting and splitting and splitting and splitting and splitting. So we can say matter is made up of pure substances and mixtures. If you wanted to tell me the difference between a pure substance and a mixture, how would you explain that? Just with your definition. Yeah.
No, a pure substance is just the one thing, and a mixture is the
Exactly. A pure substance is all of one thing, and a mixture is a mixture. It's multiple things mixed together. So a pure substance, if you have a sample, every part of that sample is going to be identical. And if you have a second sample of it, that second sample is going to be identical to the first one. It's always exactly the same. But we can break pure substances down further. We can have elements, or we can have compounds, okay? An element is a substance that cannot be broken down any further and remain what it is, okay? Think of it as the simplest building block that we can have. Everything that has matter around us is made up of elements, different combinations of elements. But the element itself is that most simple building block. You can't go below that. All known elements are on a periodic table. This one is so old that there are probably a few known elements that aren't on there, but they're way at the bottom. That's well past anything we're going to do. We probably won't go much below there, okay? So for us, this is up to date. We can treat it as up to date, okay? So if it is up here, it is an element. If it is an element, it is up here. There are no exceptions, okay? If it is not up here, it is not an element, okay? And if it is not an element, it is not up here. It's a periodic chart of the elements, okay? So you can look up there. Even if it's up there, element, okay? This is the easiest one to figure out which way you fall. If it's up there, it's here. If it's not up there, it's there. So this is the periodic table. This one's a little more up to date. Yeah. This one goes up at 112. That one stops at 107, and 107 doesn't even have a name yet. Okay. Is there a date on it? 87. That's not that old. It looks like it's from the 60s. Funny side story. My grandfather was a chemist, and he gave me one of his old chemistry books, and there were like 26 elements. I'll probably be that out of date in 50 years also, but what are you going to do? So, as you can probably guess, we can break down our elements more also. There are metals and there are non-metals. Again, this is another, if it's a metal, it's here. If it's not a metal, it's a non-metal. This doesn't have any other definition other than not a metal. Okay, this is the catch-all of everything else. So I haven't told you yet what a metal is and what a non-metal is. But you do that yourself all the time. So let's just look at these pictures and try to figure out if they're metals or non-metals. This is phosphorus. Would you call that a metal or a non-metal? Well, copper. Metal or non-metal? Metal. Bromine? Nickel? Lead? Gold? A little more tentative on that one. It's a precious metal, right? Precious. It's a metal. How about carbon? Non-metal, but not quite sure on that one. Aluminum? Sulfur? And tin. So you were right on all of them. But we haven't even learned what a metal and non-metal is. How could you tell? What about the look?
Shiny, kind of light.
Shiny.
I'm sorry.
Highly scientific word. Shiny. Okay? Believe it or not, that is the definition of metal. Shiny.
Shiny, yeah, that was good.
He was in the first lecture last.
No, I didn't remember that, I promise you.
That's why I dropped it.
Yeah, no, I didn't. I don't remember that, but
But you're right. That's what everyone was doing. They were looking to see if it was shiny. You're just the one who said it.
yeah.
So everyone. Okay. So there are two ways to define something as a metal: shiny, and then whether it conducts electricity. You can't tell whether it conducts electricity by looking at it. I can't. If you can, you don't belong in this class. Okay. You belong accepting a Nobel Prize or saving the Earth from world hunger or something. I don't know. So if it's shiny and it conducts electricity, it is a metal. If it's not shiny or it doesn't conduct electricity, it's a non-metal. Non-metals are dull. Non-metals do not conduct electricity. Let me go back to carbon. That one's all, some of them are a little tricky. If you look at that, you could make a case that that's kind of shiny, right? I mean, you can see some light reflecting off of it. It's ambiguous. It's hard to define, but you can probably look at that and say, those are shiny. That's not shiny, that's just some light reflecting off of it. You can't put that into words. It's sort of the difference between shiny and reflective or sparkly, okay? But you know shiny when you see it. But in the end, if you can test whether it conducts electricity, that would not conduct electricity at all, so that would be definitive proof that it's not a metal, okay? Selenium, that doesn't look all that different from that either, does it? But that one, you can look at that and say that's shiny, and you can look at that and say that's not shiny. So these were the elements that we looked at, okay? So we said phosphorus was a what? Non-metal. Phosphorus is right here, okay? Gold was a metal. Gold is there. Carbon was non-metal. Carbon is there. Copper was metal. Or it's right in here somewhere. There. There's copper. Bromine was non-metal. That's there. Aluminum, metal. Here. Sulfur, non-metal. Nickel, metal. Lead. Right in there. There it is. Lead was a metal. And tin was a metal. Did you see any patterns? Metals are on the left, non-metals are on the right. And then there's this little stair step here. The things that are on that stair step are kind of caught halfway between. We call them metalloids. Okay? So find the line. Anything on the line is a metalloid. Anything to the left is a metal. Anything to the right is a non-metal. That's your cheat sheet for figuring out whether something is a metal or non-metal. Just look at the periodic table. So these elements exist as atoms. An atom is the smallest piece of an element that you can get and have it still be that element. We'll talk about what makes up an atom. There are smaller pieces than an atom. But once you break it past that point, it is no longer that element. Okay? So we'll talk about how we represent atoms, but a lot of pictures are just going to be spheres. That's the easiest way and the most effective way to draw an atom is a sphere. And so these elements in the periodic table, they all have a name and they have a symbol. Most times the symbol is pretty easy. Carbon is C, calcium is Ca. The symbol is either going to be one letter, like hydrogen, or two letters, like lithium. Okay? A lot of them make sense, but some of them don't. Iron is Fe. Where does that come from? Ferrous. And where does ferrous come from? Latin. It's Latin. Or, the difference between ancient Latin and ancient Greek, I'm a chemistry professor. I don't know that. But it's Latin, okay? So a lot of these were either originally named in Latin, or the person who discovered them said, I'm going to sound smart, I'm going to name it in Latin. So we get stuck with iron being Fe. These are some of the common elements that have weird names. So copper is Cu, gold is Au, iron Fe, lead Pb, mercury Hg, potassium K. You'll use potassium and copper constantly in this class. Silver is Ag, sodium Na. Sodium is about the most common thing you'll run across here. Tin, Sn, tungsten is W. Okay. So these are the weird ones that you'll run across quite often. This is the periodic table with a bunch of elements blacked out. The ones that are not blacked out, you're expected to have memorized for the quiz next Tuesday. Okay? You need to be able to go between the name and the symbol and the name. If I give you a name, give me the symbol. If I give you a symbol, give me the name. Okay? This periodic table is also in a hopefully an easier to read form on Canvas. In modules, elements you are required to know. Okay? After next Tuesday, you will not be required to have any elements memorized. Okay? Everything after the quiz next Tuesday, you will have access to periodic table. But if you have to look up the name or symbol every time we talk about an element in this class, you're going to spend your entire life looking things up. Okay? So what I did is I went through and I blacked out the elements you won't come across very often. And I'm making you remember the ones that you will come across often in this class. Okay? So after next Tuesday, they don't have to be memorized, but you'll have a great head start for not having to look them up every time you need them for the next 15 weeks. So when we do the quiz, that's going to be up there, but you'll have to turn your chairs 90 degrees and face that way. Okay? So if you literally have eyes in the back of your head, more power to you. But no mirrors, nothing like that. You actually have to have eyes in the back of your head. We can take those atoms, the atoms are the smallest building block of an element, and we can put them together. And if we take more than one atom and put them together, we get molecules. And that molecule is made up of at least two atoms, and they have to be locked into position. So you can see here, they're locked next to each other. Here there are three of them, they're locked in a line. They have to be locked into position. If they're just flying about next to each other, that's not a molecule. And the atoms that are bound together, they can either be from the same element or from different elements. So just based on color, we can see here these two atoms in that molecule are probably the same element. That's how we draw it on the slides in the homework and things. If it's the same color and the same size, it's the same element. So here, these are two hydrogen atoms, making a hydrogen molecule. This is one of these black ones and two of the red ones. Let's say, you could say that's H2O. You could do that, yeah. It could be CO2. Anything that has two of something and one of another thing. So we take our pure substances, defined elements, broke those down into metals and nonmetals. But this has more than one element in it, right? So we're not over here anymore. Now we have to come back to these compounds. A compound is a pure substance, but it has more than one element in it. If you have something and it has more than one element in it, and it's a pure substance, it's all something, it is a compound. So water has hydrogen and oxygen. It's a compound. carbon dioxide, CO2, it has carbon, it has oxygen. It is a compound. But hydrogen gas on its own, or oxygen gas on its own, oxygen gas is O2. That's a molecule, but it's all oxygen. That is not a compound. So these are some examples of compounds. This is iron pyrite. It has iron and it has sulfur. They are locked into place. This is a compound. But if you take some sulfur and some iron and mix the two together, you didn't make a compound. You made a mixture of iron and sulfur. This is a magnet. You're just pulling the iron right out of the sulfur. You didn't make anything. You just mixed two things together. If you put a magnet on that, you're not going to be able to pull the iron out of it. And when you take two different elements and you make a compound, how that compound behaves, how it looks, is entirely different than the elements that you put in. So, anybody, what does hydrogen look like at room temperature? It's a gas. It's a gas. What does oxygen look like at room temperature? It's a gas. What does water look like at room temperature?
Liquid.
It's a liquid. That's nothing like hydrogen or oxygen. So water is a compound, and through special processes, we can break up compounds. So we can break up water using electrolysis. All you have to do is push a whole bunch of electricity through water, and you can actually break it up into hydrogen gas and oxygen gas. So this is water hooked up to a source of electricity, and we're getting hydrogen gas and oxygen gas collecting in these two tubes. We haven't gone over this yet, but can anybody tell me which tube has hydrogen and which one has oxygen? Why?
Because there are two hydrogen molecules for each.
Exactly. So, if we have H2O, that 2 means that there are two hydrogens, and that O is only one of them. There's an implied 1 right here. We don't write the 1s. There's no little number, it's a 1. So there are two hydrogens for every oxygen. So when you break it apart, you're going to get twice as much hydrogen as you are oxygen. And there's twice as much gas in this one than there is on that one. Okay. So sand is another compound. Silicon dioxide. One silicon, two oxygens. That's what this means. Again, there's an implied 1 on the silicon. There's 1 of them, there's a 2 on the oxygen, so it's 1 silicon for every 2 oxygens. So here are some elements and compounds. We're just going to try to make sure we can identify which ones are elements, which ones are compounds. So is that an element or a compound? How do you know? It's helium, it's right there. If it's up there, it's an element. You're done. What about that? How do you know? There's two different elements there. So it's a compound. What about that? Why? Two different elements. There's sodium, and then this is chlorine. In a later lecture, we'll talk about why it's I did not E, but this is chlorine. And then there's copper. Element, compound. Or compound. I swear I heard a lot of people say compound. Why is it an element? It's up there. Okay. So on that picture where we had the iron and the sulfur just mixed together, that was a mixture. Okay. A mixture is when we take two things, whether they be elements or compounds, doesn't matter at this point, and we just mix them together. We can separate these things out without needing any special process. You don't need electrolysis. On the one picture, we just put a magnet over top and pulled the iron out of it. If you can separate something by a physical process, you don't need a chemical reaction. It is a mixture. Pencil lead is a mixture. There are multiple things in there, but if you took some time, you could probably separate them out. Salt water is salt and water. They're not combined together in a compound. It's salt in water. And then air is a whole bunch of different gases mixed together. So we can separate the salt from the water. All you have to do is let it evaporate. The water will evaporate off, the salt is left behind. That's exactly how we get table salt. And anything we do with road salt or anything like that, they just evaporate ocean water, and you get salt. So, probably can't believe it, but we can actually break down mixtures into two different categories. This is probably the trickiest one because it's the most ambiguous one. There are homogeneous mixtures and there are heterogeneous mixtures. Homo meaning one, hetero meaning more than one. So homogeneous mixtures are the same throughout. Salt water is an example. If I have a glass of salt water, the salt water at the top is exactly the same as the salt water at the bottom. There's no difference. But if I add sand to water and I mix it up, for a split second, it's pretty homogeneous. If I set it here, what's going to happen? It's going to settle. Eventually, there's going to be more sand at the bottom than the top. That is not homogeneous. That's heterogeneous. Okay? Those are not ambiguous. And here and in the homework, you'll start to see some of the ambiguity, and then you'll see it again in lab. So, we need to classify these as homogeneous or heterogeneous. We just talked about salt water. What is salt water? Homogeneous. What about lake water? See, you get, exactly. Some people said homo, some people said hetero, but you're both correct. It depends, right? So when you do this on a quiz, when you do this on homework, if you think there's any ambiguity, explain your thought process, and you'll get it right, okay? So in what case would lake water be homogeneous?
You just scoop it out.
If you just scoop it out, and say it's very clean water, in what case would lake water be heterogeneous?
Yeah, same
If you had sand to it, or it's mucky water, you scoop up a fish, or a weed or something, then it's not homogeneous, right? If you take muddy water from a river or a lake, and you set it on the bench, and come back a day later, what do you think is going to happen? Some of the mud's going to settle. Then that mud isn't equally spread among your sample. So it is heterogeneous, but if it were me writing an answer, I would pick one and explain it whether I thought it was ambiguous or not. Okay. What about tap water? Homogeneous, hopefully. What about air? Homogeneous. The air up here is no different than the air back there. What about brass? This says it's an alloy of copper and zinc. Think of it as a mixture of copper and zinc. You all know what brass looks like, right? Would you say it's homogeneous or heterogeneous? Homogeneous, unless, in what case would it be heterogeneous? What does brass like to do? Tarnish. Then it's heterogeneous. You have green stuff on the outside and still shiny stuff on the inside. What about potting soil? How would you classify that? Probably heterogeneous. There might be chunks of bark or the little white perlite, little things in there that hold the water. There might be a worm in there. I don't know. But if you wanted to, you could probably make a case for it being homogeneous. But heterogeneous is the better answer here. What about chocolate chip cookie dough? Heterogeneous. Can anybody make a case for it being homogeneous?
Take the chocolate chip out.
I can't. Sorry.
you're both on the right.
If you take a clump of dough, you know, the chips are gonna
Right.
be
So the
throughout.
chips are not metal, but you can pick out them, right? If you have salt water, you can't pick out the salt. But you can read that and say chocolate chip cookie dough. And say, does chocolate chip cookie dough have chocolate chips in it? Right? It probably does, but maybe to you it doesn't. So if you wanted to say it doesn't, just tell me your chocolate chip cookie dough doesn't have chocolate chips in it.
That's so ambiguous.
So this is what we made. We made this little decision tree. So if you have matter, you're up here. Can it be physically separated? Can you pick the pieces out? Will it settle out? If it will, it's a mixture, then is it homogeneous or heterogeneous? If it cannot be physically separated, you have a pure substance, and then you can continue to define it. Are there any of these little steps that don't make sense?
So the solution was a homogeneous mixture?
Yes, a solution is a homogeneous mixture. And we haven't talked about what a solution, the definition of a solution, but you have a general idea of what a solution is. So we can, do we want to take a break now or a couple minutes? Let's take a break now, and we will start at 7:30 on that clock. So that's 7, 8 minutes from now. That's cool. Is that free?
No, I bought it like for I just like, you know,
That's neat.
yeah.
There's in the lab, there's a very like this picture. You can't spin it and see it like that.
Yeah, I like to like I don't know.
Oh, you can actually see what they're used for.
Yeah, and it shows you different like types and stuff.
Oh.
It has it. Yeah. Pretty cool.
Okay. Did you get, you're not gonna get the bookstore, you don't, it's several years old, so you're probably not gonna find it in any actual stores. Did you get either of my messages about the book? There's an ISBN in there, if you ever ordered a book online, you need to go either Amazon.com and then buy it from, if you bought anything used from Amazon, just go there, and you'll find it, and it'll say like new, or very good, or good, acceptable. You can choose what quality you want, choose what price versus quality. The other one that I like is half.com, is owned by eBay. You just search that ISBN number, it'll bring it right up. Does anybody know Inez or Sergio?
No.
you class as all,
No,
then
matches
you'll
in
have to
like.
do it for drop.
Oh, okay, drop
Have to drop that one.
Okay.
In the lab, you'll do the makeup for it, and then you'll get the data from someone else, do the post lab.
Okay. Yeah, so I'll just drop that. Or not be fine.
Okay.
Okay. What about, will I like to make up with Dr. Wilson on the next class that day?
There are no attendance points.
Okay, alright.
So I figure 40 points because you missed the quiz, 40
Yeah.
points is enough incentive.
Okay. Cool.
And the lecture will be online, so you can watch it. and
Yeah.
go back. That is the hardcover version of the one that's in the bookstore. That's the 14th edition. That's the courtesy oh, rent 60.
I was making sure that was the right one.
I got mine for 20 after shipping and
The
handling.
14th, 13th.
This is the 13th one, then.
I got mine
This was seriously, it was $1.
for 13.
That's
Same
13.
authors.
It was, that was
Yeah.
$1.
For $20 I think.
No, no, I'm just saying you look it up, you're gonna.
If you were to look up there, yeah, I think we get $4 shipping.
Where did you get that one from?
On Amazon. Yeah.
I think I mentioned in the messages that it looks like the 15th edition is coming out in December. So anyone who spent $160 for the 14th edition, brand new, is going to be worth about $20 in a few months.
Then I got the email that says you're the only dummy who spent $200.
Okay. So we saw some pictures of matter, the little spheres, right? We can talk about matter on different levels. When we first started, we had pictures. We can see matter and represent matter on the macroscopic.
Sorry, I didn't get that.
I swore I stopped that. Apparently not. Okay. So we can talk about matter on the macroscopic level. The macroscopic level is what we can see. So we can describe what matter looks like by our name. We can describe what this chair or this desk or the flag or anything looks like, right? We are describing matter, but we're describing it on the macroscopic level. We can also describe it on the molecular level. Microscopes don't do much good in chemistry. Okay, so the microscopic view of matter is the same as the macroscopic. You can't see anything. So we have to talk at the molecular level. So that's kind of a conceptual. We can draw spheres. We can draw molecules. And we can also talk about matter in symbolic form using that, using our symbols. If we write Na, that is the same as drawing a sphere and saying that is sodium. Okay? So those are three different ways that we can talk about matter. The real world, the molecular level, or on paper. So this is molecular level. This is copper metal. These are our copper atoms. It's copper, so it's all the same. They're all just lined up in neat little rows. That's the molecular level representation of copper. This is the molecular level of helium. Helium is a gas. Gas atoms float around, they just fly around. So they're not lined up in little neat lines. They're spread far apart, and there's actually little zoom lines, however you want to call them. You can look at that, and you can say that author or that artist wanted me to think those things are moving. So that's a way how we can draw molecules and atoms. So here's another representation. Is this atoms or molecules? Molecules. But they're molecules that are made up of atoms, right? So that is a molecule, but that and that are atoms. Is this an element, a compound, or a mixture?
Compound.
It's got compound, got element, anybody say mixture? Nobody says mixture, okay? So we have element and compound. Who wants to defend what they say?
It's all the same thing.
It's all the same thing, but they're attached together, so does that make a difference? No, it doesn't. If they're all the same, even if they're attached, it's an element. We haven't talked about, there's these things called diatomic elements. I don't remember if we talked about that today or next week or when that is. But there's some elements that they're lonely. They don't like to be one atom out on their own. Okay? So let's say this is hydrogen. Okay? Hydrogen is one of them. You will never find one hydrogen atom flying around. They always come in pairs, like that. So that is a molecular an elemental molecule, you could call it. It's a molecule made up of just one element. So here's some more. Element, compound, or mixture? Compound. All of the molecules are the same, but the molecules are made up of different elements. So it's 4 molecules of the same compound. What about that one? Element. They're molecules, but they're all the same element. How about that one? Mixture. They're different elements, but they're not connected together. They're just mixed together. That one?
Mixture.
It's a mixture. Here we have a mixture of 2 elements. This is a mixture of what? An element and a compound. We have this element here, but we also have this compound. It's a mixture. It doesn't matter that these are both elements and this one's an element and a compound. How about this? It's a mixture. This is a mixture of what? 2 different compounds. So they're all mixtures, they're just different types of mixtures. So you know 3 states of matter. You already said it. What are they? Solid, liquid, gas. Of course, there's plasma, and then they just discovered another one, but we're not going to talk about plasma or the other one.
What's the other one?
I don't. It actually has my last name in it. That's why I remember. It's like I want to say it's something like a Jahn medal or something like that. The long time ago there was a famous scientist with my last name, and the medal they just found uses the principle that he discovered a long time ago. So they named it after him. So what would you say are the macroscopic properties of solids, liquids, and gases? What's the macroscopic property of a solid? Macroscopic in the real world.
An item, like something you can see with you.
Right. So you can see it, you can feel it.
It retains its shape.
It retains its shape. Yeah. So you can see and feel a liquid. But so those are properties, but it's not specific to a solid.
Okay.
Solids retain their shape.
They can be broken apart.
They can be broken apart. Yeah. If you got really mad on how you did, you could break one of these desks. Right.
The atoms are moving slowly.
So you're getting ahead. That is molecular scale. But you're exactly right. What's a macroscopic property of a liquid? You can see it. It changes shape. It flows. Right? What about the size of solids and liquids? If I had that, is that desk going to change size? If I have a glass of water or Coke, is what's in there going to change size?
Depending on what you drink.
Okay. Yes. If she drinks it, there will be less Coke in there. But the Coke that she drank plus the Coke left in the bottle is still equal to the amount of Coke that's in there. No. What about a gas? What are macroscopic properties of gases?
It's in air.
It's in air. What else?
It expands to fit the container.
It expands to fit the container. Her Coke doesn't expand to fit the container, right? Solids don't expand to fit the container. The size of a gas is the size of the container, right? So that's a macroscopic property of a gas. But what else?
Color.
Color. What about color?
I like green probably. Green, light,
There are green gases. There are yellow gases. A lot of them are clear, right? I mean, all of the gases in here are clear. Probably if you're seeing a colored gas, you should be running. Okay? Generally, those are not good things. Like if you mix bleach and pine sol and you see yellow gas coming off, run. So getting back to the molecular scale, how would you describe these at the molecular scale?
The atoms depend, or the atoms move depending on the state.
Right. And how do they depend?
When they're solids, they're usually moving very slowly or not moving at all. When they're liquids, they're moving somewhat, and then gases are moving rapidly.
Exactly. So in a solid, remember that picture we had of the copper metal? They were in neat little rows. They sit there and they just kind of shake. They don't actually move, they just shake. If you have a liquid, the atoms are still close together, but they float, they move around, which is why liquids take the shape of their container. They move to fill all the spaces. What about in gases? Gases are way apart. They're just flying around completely independently of each other. They're just minding their own business. So this is basically what we just talked about. Shape, volume, gases change their volume with pressure. We'll talk about, that'll be a whole lecture later on. Liquids actually do change very, very, very slightly under pressure, but it's nothing we can see with our own eyes, whereas you know that you can compress a gas. And then how the particles are moving. Solid, they're not moving. In the liquid, they're moving a bit, and the gas are just flying. I think we basically covered that. So this is one way that we use the ability of gases to be compressed all the time, right? We compress air into our tires. If you have a tire that has gas that looks like that, you're probably not riding anywhere very fast. So you pump more air molecules in until it looks like that. And we'll talk about later on we'll talk about how that deals with pressure and temperature and all those things in the gas laws. But we also know that these things change back and forth all the time, right? If we leave water out and come back later, a week later, what's going to happen? It's going to evaporate, right? And so these elements and the compounds can change between states. So there are multiple changes going on. What's happening?
The water is cold and the air outside is warm. So
Right.
It's condensing on the glass.
Right. So you know that if you put a cold glass of water on a table, you get condensation. The water from the air will condense on the cold glass, right? What's also happening at the same time to the water in the glass?
Well, there's ice and melting.
Right. If there's ice, it's going to be melting.
It's gonna start getting warmer.
It's going to get warmer. And as it gets warmer, what's going to happen? It's going to start evaporating. So if there was ice in this glass, you would have solid water turning into liquid water, right? You would have liquid water evaporating out into a gas, and you would have gas from the air turning into liquid water on the outside of the glass. Yeah.
What happens, I hope please don't let me off, but I'm just saying, when water gets stale, like, you know, when you leave it out and it tastes different, ain't that, like, does water?
My guess is what's probably happening is when you leave water out, we'll talk about this later on in a more scientific sense, but gases can actually go into liquids, including water. So if you leave water out, it's going to absorb things from the air, and there may be things that have taste. Like when you leave a glass of milk in the refrigerator, it never tastes the same when you take it back out, right? It tastes like whatever else is in the refrigerator. That's probably what's going on.
Okay. Even if it's bottled water?
If it's open,
Okay.
yeah.
Okay.
Or if the plant was smelly when they sealed it up,
Okay.
your water may taste bad. So we have solid, liquid, and gas. When we write out formulas, and we're not really doing that now, but when we write out formulas, we have to say what state all of these things are in. And so we do it with these little state symbols. So we're just going to use water as our example. So if I want to say that I have solid water, I put H2O and S in parentheses. If I want liquid water, there's an L. And if I have gaseous water or water vapor, there's a G. Those are simple, right? It's just the first letter. But we're also going to have these aqueous things. So if I have salt, anybody know the formula for salt? It's NaCl, it's sodium chloride. NaCl, at room temperature, what state is that? It's a solid. If I dissolve that in water, we call that aqueous. Aqua, water. If something dissolved in water is aqueous. So I can say NaCl, AQ. Can people in the back read that? Okay. So it's NaCl, then in parentheses, there's AQ. That means that it is dissolved in water. Okay, so there has to be water. We didn't write that there's water here, but we said it's aqueous, so there must be water there. So this is our sodium chloride solid. On the macroscopic scale, describe to me what sodium chloride solid looks like. It's grain. It's made up of grains. What else? It's white. What else? It's crystalline. What do you think would happen if you could squeeze it? It would break. What would happen, and what would you, if you couldn't squeeze it hard enough to break it, what would you feel? It'd be sharp because it has edges. It'd also be hard, right? It's a solid, it's hard. So those are all macroscopic things that describe salt. What does salt look like on the molecular level? Crystalline, so the atoms are arranged in a neat manner. We haven't really talked about this yet, so if you don't know, don't worry about it. So if copper solid is rows and rows of copper atoms, what do you think sodium chloride solid looks like?
Also,
Right. It's alternating sodium and chloride. What does the subscript on the NaCl tell us? There is implied subscript, right?
There's just one of each.
There's one sodium for every one chloride. So it is alternating sodiums and chlorines in rows. That's what it looks like on the molecular scale. How much are they moving? Not much. They're just shaking. They're solids, right? How close are the atoms to each other? They're very close. Solids are very close together. So you were describing properties. When you were talking about the macroscopic salt, you were describing properties of it. And we have physical properties and we have chemical properties. And then we have physical changes and chemical changes. Okay? An example of a physical property is color or odor. A physical property is something that you can determine about something without changing it. You can look at this pointer and tell me what color that is. And the pointer hasn't changed at all, right? If she opens her Coke, you can tell me what that Coke smells like, but you haven't changed that Coke at all. That's a physical property. It's something that you observe without changing. We also call them qualitative properties. It doesn't matter how much you have. If this pointer was twice as big, it'd still be the same color. If she had twice as much Coke, it would still smell the same. Opposite of that are quantity, numbers. These do matter how much you have, but they're also physical properties. Mass. If I put one of these on a scale, it's going to give me the mass. I didn't change it. It's still a physical property. But if I put two of them on there, I now have more mass, right? So that's a quantitative property. Volume, how much space something takes up, is quantitative. Density, it's mass for volume. We'll talk more about density next week. It's quantitative. And then temperature is also quantitative. We can put numbers on these. If you can put numbers on something, it's quantitative. Unless you're an HTML web designer, you can't put numbers on colors, right? If you put the hex code on it, that's not quantitative, it's just another name. You can put numbers on mass, volume, density, and temperature. A physical change is a change that changes physical properties. But you don't change what it actually is. Can anyone give me an example? Breathing.
Ice cube.
Ice cube. What about ice cubes?
Because you're changing the state of it from liquid
Right.
to solid, but you're not changing.
Freezing ice cubes. You have liquid water, then you have solid water. They're very different. They have different physical properties. One's hard, one's not hard. But they're still H2O. At the beginning, you had liquid H2O. At the end, you have solid H2O. At the molecular level, nothing changed. All that changed was the observable properties. Do you have a question?
Yeah, I was gonna ask, what about dry ice?
Dry ice turning into a gas?
Yeah.
Yeah, that's another physical change. Dry ice is CO2, it's carbon dioxide, you have gas. That's just a special case. CO2 is able to go straight from solid to gas. So instead of going from liquid to gas, you're going solid to gas. But it's still CO2 when you start, and it's CO2 when you end, so it's a physical change. So this is exactly, basically what you talked about. It's still water, but this is evaporation of water. This is liquid water going to gas water. It's still water, it's H2O. That hasn't changed, it just behaves different. And this is CO2. This is called sublimation. Going from a solid to a gas is called sublimation. Most of the other ones you know. What is liquid to a gas called? Evaporation. What about gas to a liquid? What do you call the water on the outside of your cold glass? Condensation. What about liquid to a solid? What do you call that? Freezing. Think about water. Water is the best example. If you turn liquid water into solid water, you're freezing it. What if you turn solid into liquid? Melting. Those you know. You don't have to memorize those. You know those. There are two that you don't know. Sublimation is one of them. That's solid to a gas. We don't have this happen all that often. So this is molecular level representation of our solid CO2. If we were going to draw the gas CO2 over here, what would it look like? They'd be spaced out. They'd be moving. What would the molecules look like? The molecules themselves. They'd be the same, right? So if you're far far away to see this, but there's a black and two reds stuck on it. And there's one of those next to one of those, next to one of those, next to one of those. Here, it would be just those, a black with two reds, but they'd be spread apart. So they look different. They behave different. But they're still CO2. So that's what it would look like. The opposite of sublimation. Sublimation, we said, was solid to a gas. The opposite is deposition. Okay? I remember that from the root word deposit. okay? You're gonna see this in lab, I think it's this week. It's going to, out of thin air, literally out of thin air, solid is going to get deposited on something. It's gonna look just like the water condensing on the outside of the ice water, but instead of being liquid, it's going to be solid. Okay? We'll take iodine. Iodine at room temperature is a chunk. It's just a solid. We'll heat it, and it'll go straight from a solid to a gas, and then we'll put literally, basically ice water in there, and on the outside of the ice water, the iodine will reform as a solid. Okay? So whether deposit helps you remember that or not, it's up to you. Whether you want to try to make sense of it or just flat out memorize it, that's up to you. But you have to know it, okay? These I wouldn't worry about too much. You can figure those out. The thing about water, these make sure you look up. A chemical change. So we said a physical change is something that does not change the molecules themselves, right? A chemical change is going to change what molecules we have. The more common name for this is a chemical reaction. A chemical reaction is a chemical change. You're taking something and changing it into something very different. If you take what does a new penny look like? It's shiny. What does an old penny look like? It's dull. It's not, it's darker, right? What is a penny made of? Copper. Does anyone know what's on the outside of an old penny?
Oxidation.
Oxidation, exactly. You make copper oxide. So you went from copper, you now have copper oxide. That's not the same thing. Does everyone see that? Yes, it looks different. So you can't say it's not a physical property just based off, physical change based off that. But copper and copper oxide are not the same thing. Copper you would write like that. Copper oxide is that. Those are not the same thing. It's a chemical change. When you burn gasoline, that is a chemical change. What do you know what you, at least one thing that you make when you burn gasoline? What do you make?
Carbon dioxide.
Carbon dioxide, that's the one I was going for. I didn't see fire coming. I should have seen fire coming. Chemistry would be easier if there are elements where fire, water, and air. Or earth, wind, and fire, there we go. If we had earth, wind, and fire, we would be done in one class period. But we're not earth, wind, and fire. If you react hydrogen and oxygen, you can make water. Just like we saw taking water and separating it into hydrogen and oxygen, if you take hydrogen and oxygen and react them, you get water. Has anyone ever seen, well, you've seen the video of the Hindenburg, correct? The Hindenburg? Don't tell me I'm that old. The Hindenburg was a Zeppelin, which is basically a German blimp, okay? When you want to make a balloon float, what do you fill it with? Helium. Hydrogen works better than helium, but hydrogen is incredibly flammable. So imagine a blimp filled with hydrogen on fire.
You just showed us the video.
Just look up YouTube. It's a very famous. Have you ever heard the phrase "Ode to Humanity"? It's from that video. Okay. You've never heard the phrase "Ode to Humanity"? Yeah. Okay. Look it up. Okay. It's a blimp burn. Okay. But if you take hydrogen and you burn it, burning is a reaction with oxygen in the air. So you're combining the hydrogen from the blimp with the oxygen from the air, and you actually make water. We'll do this in lab, not in blimp scale, but in test tube scale. Okay. So you'll get hydrogen in a test tube, and you'll burn it. After you burn it, there will be water inside the test tube. okay? So you're converting hydrogen and oxygen to water. So the hydrogen gas is H2. Oxygen gas is O2. Water is H2O. This is not the same as simply mixing those two things together. Does everyone see that? That's a completely different thing. It's a chemical change. So that's exactly what we just did. Hydrogen reacting with oxygen. That's how we write a chemical reaction. We're not that far yet. There are ways that we can look at something and get an idea that a chemical reaction could occur. We can't see that there are hydrogen molecules and oxygen molecules to begin with, and then water molecules to end with. We can't see them. We have to use our senses and measurements to try to figure out whether a chemical reaction happens. Usually, bubbling means a chemical reaction. The obvious exception is boiling. We said boiling is a physical property. If you take two things at room temperature and they're not boiling, and you mix them together and it starts bubbling, they're not boiling, they're reacting. Like vinegar and baking soda, right? Neither one of those is boiling at room temperature, but you put them together, you get bubbles. If you get a permanent color change, permanent being the key word, that is a chemical reaction. The copper on the outside of the penny, you can't take that tarnished penny and easily do something to it and turn it back into a shiny penny. If you polish it, all you're doing is you're scraping the outside off. The outside is still tarnished. It's just now on the table somewhere. Or if you have a sudden change in temperature. Anyone ever used the little hand warmers? The things you open up and they get hot? That's a chemical reaction. It wasn't hot before you opened it, right? You opened it, it got exposed to the oxygen in the air, and a reaction happened. It gets hot. Same thing with the instant cold packs. You get a reaction, and all of a sudden, you get a temperature change. You didn't heat it to make it hot. You didn't cool it down to make it cold. It seemingly did it on its own. That is a sign of a chemical reaction. Yeah?
I have a question. One thing I was wondering what could cause this, like if sometimes if you get a water bottle out of the fridge, if it's cold enough, then when you shake it, it seems like it freezes. Is something.
That's being called supercooled. So, how do I want to? In order for water crystals to form, they have to have something to form on. Okay, this is a very common. We won't use this in this class, but this is something that scientists can use to their advantage. For crystals to form, they have to have something to form on. So the inside of a plastic bottle is incredibly smooth. So if you put that water in the freezer and you freeze it, it freezes pretty slowly. That's key also. It gets down to freezing temperature, but there's nowhere for the crystals to form because it's on a smooth surface. So it just keeps getting colder and colder and colder. You reach into the freezer, turn it upside down, you introduce an air bubble into it, because you turn it a little bit air top, then bubbles through it, right? You just created somewhere for the crystals to form. The first one forms, and then the whole thing goes. That's the same thing. Has anyone ever heard not to boil water in the microwave by itself? The same thing happens with that. It gets superheated. For something to bubble, to boil, you need something for the bubbles to form on. So Mythbusters did this a while ago. We take a bowl of water, and the conditions have to be just right, but it can happen. You put it in the microwave, and it gets really, really, really hot, to the point that it should be boiling, but it's not. You take it out, and then you put a spoon in it or something, and then all the bubbles form on the spoon, and it basically explodes into boiling water in your face. This happened to me in lab a few months ago. We had this heating apparatus, and in it, I put little samples in it to get them hot. And I have a thermometer in it so I can measure how hot it is. And the thermometer sits in a test tube full of water, and that kind of buffers against very fast air currents and things changing the temperature of my thermometer. But it got really hot. It was boiling, but it wasn't boiling. And the thermometer had turned itself so it was facing away from me. So I grabbed the thermometer to turn it to me, and when I touched the thermometer, it moved, created a place for the bubbles to form, and the boiling water shot out on my hand. Luckily, I was wearing a glove, so it was hot, but it kind of deflected off and I didn't get burned. But if I had reached my head over there or something, yeah. Oh. But don't do it.
I have a question about like air vacuums with negative mercury units. How does that work when you put water in there and you add the vacuum and it boils it?
We'll talk about that in depth later.
Okay.
But basically, the boiling point of something is dependent on the pressure above it.
Okay.
That's why on a mountain, water boils at a lower temperature.
Gotcha. Okay.
More fascinating questions. Okay. So this is boiling water. Physical change, chemical change. Physical, why?
This is not changing.
It's still H2O, right? It just changed state. You're going to see this. You're probably going to be asked this on homework, on quizzes, on final exams. State changes are physical changes, okay? Because when you're writing exam questions, you can't always ask about chemical changes, but there are only so many physical changes to choose from. So everybody always chooses a state change, okay? So you'll see it over and over and over again. This. So this is what we're starting with, this is what we're ending with. Is that a chemical change or a physical change?
Chemical.
Why?
Because it's starting at one thing, turning to
Right. We start with O2 and CH4. CH4 is actually methane. And at the end we have water and CO2. Those two things that we ended with are very different than the two things that we started with. That is clearly a chemical change. This is actually the burning of methane. So what would you observe if you were doing this? What would you observe that would tip you off that a chemical change was happening?
You're not looking for fire, right?
Something having to do with fire.
Is it the color?
Oh, the gas.
You could do the gas. You could do the gas was not what I first thing came to mind. But that you don't start with the gas, but you make a. Oh, actually, you do. You start with oxygen and methane are both gas. So in this case, you're on the right track. But in this case, it doesn't work. What were there were three things that we said to look for a chemical change: bubbling, temperature. What happens when you burn methane? It's hot. That's what you're looking for. Fire is hot. That is your lesson for the day. Fire is hot.
Will that be on the quiz?
No. But you can impress your friends, you know. Physical change, chemical change. Physical. This is our CO2 sublimation again. It's CO2 here, it's CO2 there. This is another polling thing. So you get your phone out. I need to change the website. So here's a picture. You don't know what that is yet, okay? Maybe you've done this and you know what that is. But you're just going to go off the picture, and is that a physical change or a chemical change? You can either go to the website and choose one, or you can text, if you say it's chemical, you text that number to that number, or physical, you text that number to that number. Again, it's anonymous. If you don't want to do it, you don't have to do it. So what we're going to do is we're going to look and see what people said, and I'm going to give you a little bit of information about what this is, and we'll redo it. And we'll see what people say. Then we'll actually really talk about what's going on, and we'll see if people change their mind. Anyone still sending? Okay. Let's take a look. It's like there's 7 chemical and 6 physical. I'm not sure if there's one. Oh, I bet you that's the number you're supposed to call first. Okay. So we've got basically 50-50. How do I call it? Okay. So what this is a coffee filter. They folded it up into a kind of a triangle thing, and then they took black Sharpie and marked the tip of it, and then opened it back up until it was kind of in a cone shape, put the tip in water. So the water soaked up through the coffee filter, starting at the black tip and up. And that's what you ended up with. Physical change or chemical change? Send it. You probably figured out it was a coffee filter when it said coffee filter art. You know, it looks like a coffee filter, so probably. Anyone still sending? So we've got 10 chemical, 4 physical, 5 physical. Does someone want to defend chemical change? Go ahead.
I guess you could never change it back to a white filter. Like the marker, yeah, you can never put it back to its original state.
I see where you're
back
going.
to the black dot.
One of the color characteristics of a chemical change is a permanent color change. So he's saying that's clearly a permanent color change. I mean, how on earth can you undo that? It's a permanent color change, right? Anybody else have another reason for calling it a chemical change? Anyone want to defend physical change? Go ahead.
If you add Sharpie to it, then the Sharpie is the same throughout. It's just the dispersion that's affecting the light. It's the same thing. You haven't changed either the chemicals, you just mixed them.
Okay. So what we're going to do is we're going to break into groups, and you're going to try to convince the rest of the people in your group that you are right. And then we're going to break back out of the groups, and you are going to vote completely independently. So if you think you're the only intelligent person in your group, and you're the only one who has it right, you can vote however you want to vote. Okay? So let's do those 2 rows as a group, these 2 as a group, and then these as a group.
Yeah, where's the water going? From the Sharpie, that's originally supposed to be going to the coffee filter. I mean, that's kind of old enough. Where's the water? Was originally supposed to be. I mean, it was black, and then it turned into multiple different colors. So, I mean, right there. It's like, you did a happy history, that the colors came out black. That's just
By doing what?
Yeah, just
But they had a way to do it.
I think it wasn't justified.
Yeah, but I was saying,
Yeah,
when
so
you
let's
started
say
with
you
the
get all
How
those
can you
colors
have
on
black
Sharpie
marks?
paper.
Black is a
Well, if you bleach it, that's a chemical change, right?
Yeah.
Well, that's not sharp,
Yeah,
right?
black
You're adding color to it,
there.
changing color.
Because he said, the more colors,
I'm just throwing that out
So when
there.
you think about it, now, bleach is a chemical change, you're gonna change the color, it's the same thing. If you had a bleach Sharpie and added it to it, if you added more water to it, the color would be permanent. It wouldn't, it isn't a permanent color.
I just thought it was
It's
different.
It's permanent if you add more chemical, if you add the chemical change first.
That's not, I don't think that
It would change
justifies.
again if you added more chemicals to it. It would, but so it's still a chemical change, you had to add more chemicals.
Okay, you said you molecular. Ain't no molecular.
Is this group done? Is this group done? They're never gonna be done.
I'm not.
There's a high level of debate over here. Okay, so let's go back. You can ignore everybody else. Give the, actually, I have to clear it first before you send it. Now you can send it, whatever you want to send. Yeah.
Will we actually try this? Does that make?
You can do it at home. If you have a coffee filter and a black Sharpie, go home and do it.
What kind of that sound?
I just want to sleep.
can't waste my coffee.
This is a nobody did this for 4th grade science fair?
Fourth grade. What'd you do?
For 4th grade, I measured which material, my dad worked in a nuclear power plant at that time, so I measured what materials blocked radiation better. I had a Geiger counter and everything.
4th grade?
4th grade.
Oh, that explains a lot.
What, dude, the story is, if you ever heard of the dinnerware, the plates made by Fiesta, Fiesta is a company of plates. They actually used to use radioactive paint, okay? They don't anymore. But literally, what my radiation source was a piece of an old plate. People used to eat off this stuff.
Yeah, that's messed up.
I mean, it's kind of like the old watch dials that had radiation on them. The plates used to be radioactive. So I had a Geiger counter and a piece of a plate, and I just put random things between there and saw what happened. 5th grade, I measured.
Did you win?
No, it's elementary school participation thing. So they have first place, 50 people get first place, 50 people get second place, and there's.
So you didn't get first place?
I got first place, but so did 49 other people.
Kind of what's better about
1
it.
out of 50.
That wasn't good enough for you?
That's why I became a
You just seem
scientist.
like coming down about that,
To prove everybody.
No, in 5th grade, fifth grade, I measured which fishing knot was the best, and I got into the first place. But
I didn't mold on
Sorry, I feel you.
okay, so let's see what happens.
Oh,
We're
man.
back where we started.
Alright, what's the answer?
Okay. So, the way to work this out, what is black Sharpie? A combination of all the colors. Black pigment is not black pigment. It is all the other pigments mixed together, right? So when you started with the black tip, the purple, the blue, the green, the yellow, the orange, they were all there. Just because they were on top of each other, your eyes saw it as black. So all you did is you put the purple ones out here, the green ones out here, the yellow ones out here, the red ones there. Everything is exactly the same, it's just in a different place. So our eyes see them differently. So, is that a chemical change or a physical change? Physical change. But we said a chemical change is a permanent color change. How on earth can you undo that? That's permanent, isn't it?
You don't have to undo it. You can change it further, and it's not a permanent change. If you put more water on that, it would separate even more, and it's not permanent.
Okay, yes, that's true. You can undo this. How?
So you can or
You can.
You
Can by changing it more.
White Sharpie.
You can condense that back into a black dot.
Just like
There's a real world way of doing it, and then there's a make-believe way of doing it.
So real world, you just color it all black.
You're thinking the right way.
I just throw it away and forget about it.
So what would happen? I mean, these are made up. The rings are made up of different molecules, right? So you have to get the molecules back in the same place as each other. So what if you were microscopic? You could just grab them one at a time and move them back to the center. I mean, if 100 years from now we had basically molecular level tweezers, you could do that. But that's not an unfeasible thing to do, right? We just don't have the technology to do it. But there is a way that you can go home, make that, and undo it. It's probably not going to look as neat as it started, but it'll be pretty close.
I mean, if it like distilled in the water and you put it back in the water and have it evaporate, in a sense.
I see, that's not what I had in mind, but yes. Because if you let it go, eventually it's all going to end up in the water. If you let the water evaporate, the colors are now mixed, they're going to make like basically a black layer, black film. That would work. How can you get back to the black dot in the center of the coffee filter?
You fold it back up and just run water to the top of it. Just have it like all
Run the water the opposite way. We ran the water out and pushed everything that way. If you put the top upside down in the water is going to go this way, push everything back together. This is called coffee paper chromatography. Chromatography is a big word. It can be simple or it can be really complicated. Basically, it's the ability to separate things based on their properties. So when you put the water in the center, all these different pigments dissolved in the water to different rates. Okay? The purple one out here dissolved very well, so it moved very well. The red in the center didn't dissolve very well, so it stayed in the center. That's chromatography. Okay? So you can do it with a coffee filter, or you can do it with the $100,000 instrument I use at work. Same principle. Okay. So here are some more things. Evaporation of water, physical, chemical. Physical, it's still water. Burning of natural gas. Chemical. Burning, it's not natural gas anymore. Melting of metal. What happens if you take that copper and you melt it? Physical. It's still copper. It just went from solid to a liquid. Turning hydrogen and oxygen gas into water. Chemical. They're different. The chemical properties are the hard ones to conceptualize. You can picture a chemical reaction. You can imagine whether a chemical reaction happened. But what is a chemical property? A physical property is the color, what it smells like, what it feels like, something like that. But our senses don't work for chemical properties. So a chemical property is how well and under what circumstances something undergoes a chemical change. So hydrogen burns very, very easily. That is a chemical property. What's another chemical property that someone can think of? What's a chemical property of water? Think about, I just said hydrogen burns easily. Water doesn't burn easily. That is a chemical property of water. Okay?
But you can burn water?
Well, I guess you could take that statement that way. Yeah, you cannot. Water does not burn. I can't think of a situation that you could burn water. But okay. Hydrogen burns easily. That's our chemical property. Helium does not react. Okay, that's why we can fill our balloons with helium, and they don't burst in the flames. Okay? We'll talk about this, I think, 2 weeks from now. Everything all the way to the right here, they're called noble gases. They're stuck up. They don't like to interact with any other element. They don't react. Iron rusts. That is a chemical property. If you have an iron nail and you set it out, we're going to have to use iron nails in the lab all the time because they're cheap. Iron nails rust, right? Your car rusts. Silver tarnishes. You have a silver necklace, what happens to it over time? It gets dull, and if you don't wear it at all, what happens to it? It turns green, right? Silver, the tarnish will be green. If you wear it, eventually you keep knocking it off, so it gets dull. But you don't get enough to actually be green. And gold is very unreactive. You don't normally see dull gold. A gold ring gets dull because it gets scratched. But there's no, it's not reacting, it's not tarnishing, right? Gold is unreactive. That is an example of a chemical property of gold. The last thing for today is scientific method. How many people have learned the scientific method? That's fourth grade science fair, right? But fourth grade science fair didn't make you memorize terms and determine what part of a statement is what, okay? That's the level we're going to take it to. So in science, we use a scientific method. Normally we look at something, we get as many observations as we can from it. We say, make a hypothesis. A hypothesis is a testable, educated guess. I look at that table, and from my many years of experience, I say, I bet you that's a solid. Okay? I hypothesize that's a solid. How can I test that? Kick it, hit it, right? If it's a liquid and I hit it, it's going to splash. If it's a gas and I hit it, my fist is going to go right through. It's clearly a solid, right? I just tested my hypothesis. In science, we also have laws and theories. Laws and theories are where it gets tricky. This is another slightly, it's not ambiguous, but until you really get a good grasp of it, it can seem that way. So observation, we can experiment or observe. I observed the desk, okay? I made one hypothesis. If I didn't make that hypothesis, and I immediately came up and I knocked it and I said, that's a solid, I could make another different hypothesis. What other hypothesis could I make once I experimented and found out that was a solid? It's not a liquid. If by being a solid, it's automatically not a liquid. What's something very, what are the properties of a solid? The shape, right? So I could hypothesize that if I put that in a different container, it's not going to change shape, right? And then I could test that. So I can either just observe, or I can experiment. Basically, in either way, I'm collecting data. We take those observations, we come up with a testable explanation. It's an educated guess. Okay? Educated guess is the long-standing definition of a hypothesis. It is the best explanation or guess that you can make with the observations and the data that you have. But it has to be testable. If you make a guess and there's no way you can test it, that is not a hypothesis. A law describes how nature works, assuming the conditions are the same, how nature will always, always, always work. A law has no exceptions. If I take this pen, this marker, and I drop it, what is going to happen? It's going to fall. That is a law. Okay? A theory explains how all of these things come together. Okay? I observe this is made of matter, right? I hypothesize that if I drop it, it's going to fall. Every time that I drop it, it does fall, and it's never not going to fall. So that me dropping this and it falling is a law. A theory explains why it falls. Why does this fall?
Gravity?
Gravity. Theory of gravity is that two things that have mass, that are made of matter, have attraction between them. You can imagine a scenario 5,000 years from now that someone proves that wrong, right? That is an explanation. We cannot prove that these two things have attraction between them other than showing that every time I drop this, they go together, right? There could be a better explanation. We, as humankind, just don't know it yet. But if I drop it, it's always going to fall. That doesn't need an explanation. That is a law. Does the difference between that make sense? A law is something that always happens. A theory is an explanation of why that happens. A theory can be proven wrong. A law cannot be proven wrong. So this is the flow chart. We make observations, we see some patterns and trends, we take that into our brains, we make a hypothesis, we propose a theory, and we either test our hypothesis or we propose our theory. Once we test them, we now have more data. More data means we now see more patterns or trends, which means we can update our hypothesis. So everyone always thinks if you make a hypothesis, you better be right. Or if someone makes a hypothesis on their fourth grade science fair project, and it turns out to be wrong, what does everyone always do? They change their hypothesis and say that's what they meant, that's what they thought was going to happen to begin with. Making an incorrect hypothesis is not bad. You make a hypothesis for the purpose of testing it. No one cares whether you were right to begin with or not. What people care about is what you tested and what you observed. So every day, professional scientists make a hypothesis, and probably 90% of the time we are wrong. Okay? But we figure out we're wrong, and then we make new hypotheses. That's how it works. Okay. So, as one last little thing for your introduction to chemistry, we have more experiments you can do. I don't know if there's music to this one. This is called elephant's toothpaste. Know what is happening. Basically, you have two important things. You have hydrogen peroxide and you have yeast. What do you think is happening? Anybody know the formula for hydrogen peroxide? H2O2. H2O2. When you look at that, what does that look like to you? It looks like water, right? What's the difference between that and water?
Extra oxygen.
It does an extra oxygen. What the yeast does is it breaks that extra oxygen off to make water. So now you have water and oxygen. Oxygen is a gas. You now made a gas in soapy water. You get a hard bubbles. That's what's happening. Because they didn't show it very well, but it's not like Coke and Mentos where it just bubbles and then goes away. It actually makes something you can pick up and throw around. And it looks like toothpaste, but there's a whole bunch of it, so it's for an elephant.
I don't even want to try it on.
It said do try it on.
Oh.
Yeah, just don't do it. Just don't do it on your expensive tablecloth. So remember, the lecture will be online probably tomorrow. The homework 1 is due next Tuesday. There's 2 parts. Multiple choice on Canvas. There is the handwritten portion on Canvas. If you want to turn that last handwritten portion in, that question, early, you can, but it has to be in PDF. Okay? On Thursday, print out the lab. Bring your safety equipment if you have it. I think that's all you need for Thursday. If you have any questions, email me through Canvas. That's always the best way to get a hold of me.
Where can we find out?
The bookstore has it. There's a thrift shop on campus. I don't know where it is. It's called Yeah, St. Sherwood. I don't know where it is. Some people find it for all the lab coats and stuff for $1 there. If you can't find it, I would go to Harbor Freight up on Main. You can get cheap glasses. You can probably find an apron there. You can go to Lowe's, but it's going to be more expensive.
Right. What was the name of this? You said that Harbor Freight, or what was it?
Harbor Freight.
Harbor
It's on the
Freight.
corner of Main and 23rd. Yeah, I don't know if you ever go on that side of town.
It's I guess it was
There's a Winn-Dixie right there.
Yeah. Okay. On Main. Yeah. That's like.
There are 2 Winn-Dixies on Main. There's one down by campus, and there's another one.
That's like near 16th.
Well, there's Southwest 16th, which is down by the Steak and Shake.
Yeah. Okay. Like I work at the VA, so like when I pass the VA going like I pass 13th going towards Main Street, it's not that one, right?
So you would go from the VA. You would go up 13th
Okay.
to 23rd. What's in the 23rd? There's the Rooms to Go Express, and there's like a Dollar Tree where Lucky's is there.
Yeah. Yeah.
That 23rd. Take that over to Main.
Okay.
And then there's a Winn-Dixie, there's Harbor Freight, and then there's some abandoned stores.
Okay. All right. Okay. Cool. All right.
Yeah.
Awesome. Yeah. Yeah. I was really because you see when I.